Thank you very much all for coming, and today I'll be talking about how over the last year or so, some of the things we've been doing with Codec 2 and related software, in particular getting Codec 2 running on an embedded microcontroller. So these are the topics I'll be discussing today. The Codec 2 project started in 2009, so it's nearly 5 years old now, and I'd like to talk a little bit about where we've come. Every year I've been presenting on this for the last two LCAs, so there's plenty of videos that talk about the codec and how it works for those of you who are interested from the past LCAs. Codec 2 has been combined with a modem and a GUI to create a package called FreeDV, which can hook up to a analog single sideband radio and be used to transmit digital voice all over the world, and that's been in fairly wide use for about a year now. I'd like to talk about some of the aspects of free speech that open source digital radio can be used for. Ask why embedded, why we'd want to embed Codec 2. It's running quite happily on a laptop and larger machines. Why do we need it on a microcontroller? And then talk about the actual process of porting Codec 2 to a microcontroller. And then talk about porting a radio to a microcontroller, which is a bit of working in the other direction. Okay, so Codec 2 is the world's only open source low bitrate codec. There's quite a few open source vocoders and audio codecs in higher bit ranges, above say 5,000 bits per second, but everything else is closed and patented in this domain beneath around 2,000 bits per second. Codec 2 is patent free. It's based on public domain intellectual property and original research that's been released into the public domain. It's competitive with closed source codecs in terms of the speech quality, the bit rate and the robustness. Two forms of robustness it's reasonably good at. One is robustness to background noise. If you're driving along in a car, you've got road noise or air noise, it doesn't completely corrupt the voice signal. And the other is robustness to bit errors. You can put it through a fairly nasty sort of radio channel and still get something you can understand out the other end. The main application for this sort of very tight compression of voice is for digital radio. Things like HF radio using equipment like this. This is a small analog single sideband radio that can transmit over the HF spectrum, and also VHF radio like walkie-talkies, that sort of push-to-talk stuff, where spectrum is very limited, so you need to compress the data to a very narrow bit stream before sending it over the analog channel. So FreeDV combines the Codec 2 speech codec with a modem specially designed for the HF channel and puts it together in a GUI application that you can run on any sort of desktop, Linux, Windows and Mac. It plugs into single sideband radios, replacing the microphone and speaker. This plugs into the laptop, and then you have a headset plugged into your laptop that you generally use to listen and talk through the system. So it lets any analog SSB radio, turns it into a digital one. That was released just over 12 months ago. It's had a few revisions. We've improved the quality through some experimentation with hams and going back and working on it. And we've now got robustness of that system approaching that of analog single sideband. What I mean by that is that compared to single sideband, it operates at almost the same sort of signal-to-noise ratios or ranges, but it's not quite as good. There's still some cases where you can get an analog single sideband signal through where a FreeDV will fall over. When FreeDV does work and lock up, the quality tends to be superior to analog single sideband because there's none of this annoying background hiss you get with analog HF radio. So I've got FreeDV running here. Now I'll just play the output through the speakers. FreeDV, as well as being able to play off the radio, can decode signals off recorded files. Sometimes when I'm debugging, I get people all over the world to record a signal off the air, the modem tones off the air, and send it to me so I can play the signal and debug it. So for this example, I'm not doing anything off the air. I've just got a signal that simulates the modem signal that comes off the air. But to get you a feel for what it does and what it sounds like.
W5 ADC, here is Victor Echo 9 Quebec Romeo Papa. My name is Bruce, Bravo Romeo Uniform Charlie Echo. I'm located in Sackville, New Brunswick.
So that's a Canadian ham radio operator putting his voice through the system, and that's the sort of quality that would come out of it. No background hiss, reasonably intelligible. I'll just give you a little demo of some of the displays. What you're seeing at the moment is a spectrogram, and if you count the vertical lines going up there, there's actually a total of, I think, 17, 8 on this side, 8 on the others, and 1 in the middle. They're various carriers that are used to send the information. They're the modem carriers. We can view that as a spectrum. And once again, you can see there's sort of 16 lines, and the big one in the middle is used for synchronization, so it's at a higher power. And that's the real-time spectrum of the signal, the modem signal. The modem signal that you hear off the air sounds like this.
And
it synchronizes very quickly.
Using the Codec 2,
doesn't require any training sequence. So that's the spectrum of the signal that you send over the air. Now, those of you who attended my modem talk will recognise this as a scatter diagram. And in this case, it's a quadrature phase shift key signal, so there's 4 constellation points you can see. The constellation points are very tight, which means it's a really good channel, as it should be. It's just a recorded file off the disk. And the 2 outer points are the high power synchronization carriers in the middle, and they're only a 2-phase signal, so they're binary phase shift keyed. And once again, those who came to the modem talk, I talked about timing and frequency offset estimation. Well, this is an indication of is estimated at a timing offset of 0.1 symbol and a frequency offset of nearly 0, maybe about 20 hertz or so. Oh, and it's just lost it. That was the end of the recording, so now it's searching to try and synchronize again. So all those little displays, they help you tune the signal, get to see what's going on. It's got a bit error rate counter along the side, so you can see the bit error rate of the signal over the channel, and things like a signal to noise ratio quality bar, plus some other features like squelch, so you can make it be quiet when there's no actual signal on the air. So that's in fairly wide use at the moment, and we're continuing to develop that. Okay, one other exciting development is something called a Whitebox handheld software-defined radio. A very talented RF engineer by the name of Chris Tester in the US is developing this. It's basically an open, hackable walkie-talkie. So a software-defined radio that can transmit and receive in a form factor that you can hold in your hand, and it's designed for fairly low power consumption on receive, so it's portable, battery-powered. Covers the upper VHF and UHF spectrums up to from 100 to 1,000 megahertz, and it's half duplex, so it's something like a push-to-talk walkie-talkie or this analog radio here. You can only transmit or receive. You can't do both at the same time, but that's pretty common for this sort of stuff and not really a problem. And they're developing a couple of versions. So one is a commercial one that will be certified to the various standards around the world, so it can be used and sold for commercial purposes. And then there'll be ham variants that are completely hackable, that you can build up your own waveforms and put your own software on. And it's running Linux underneath, and there was some talk of it running Android as well at this stage, but I'm not quite sure if it's there at that point. It's just Linux. Yeah, and so that's being developed over in the States at the moment. It's pretty exciting. And they're planning to run Codec 2 on it, as well as a bunch of other modes. And that's a picture of an early prototype. So you can see it is sort of a handheld form factor, and it's got a dedicated FPGA ASIC type chip that's designed for this sort of radio, SDR radio work on it.
What's the target cost?
I don't know. Good question. Yeah. They're planning to have production release this calendar year. Yeah. So why open radio? Why are we interested in things like open source codecs and modems and making the whole thing open rather than buying all the the fixed proprietary stuff that's coming out? One really good reason is for humanitarian applications. HF radio, this sort of stuff can be used in places where there's no infrastructure. And that could be a developing country where there's never been any infrastructure. It could be something that's been wiped out, a first world country or area that's been wiped out by a natural disaster. But this sort of HF radio will get through when nothing else does. The problem is it can be fairly expensive. The radios are fairly complex. You need power supply systems like solar. Once you start putting digital data over them, it gets even more complex. It's a fairly narrow channel and you need very specialised modems. So it's not uncommon if you used commercial hardware to pay $10,000 per site, which is fairly expensive. But with open source radio, in particular software-defined radio, much of the functionality can be defined in software. That can be open and free. So you can start talking about a few $100s for a HF radio terminal rather than 10,000 or so. If we can come up with software to do most of the radio work, we can also talk about very simple radio designs, and then they're amenable to local manufacture. So, for instance, some guys with a soldering iron in a third world country can start talking about assembling some of their own kit rather than importing it. Hams and hackers, very interested in open source radio, of course, so we want to modify, improve, tinker. The ham amateur radio community are very keen on sharing things. They have done for a long time, and they share a lot of our ethos, I guess. And no lockdown is really important. These standards last a long time, and we don't want to be locked down to any proprietary standards. And that's there's an effort on at the moment to do that in the digital radio field, to use proprietary standards and proprietary vocoders, which is why we're sort of doing this work. Another sort of freedom that's just come to light, I guess, with revelations over the past few years, is this sort of context of freedom. I think open digital radio and hardware can be a force for freedom in this area because it works when the infrastructure is down. If you've been denied access, the communication systems have been shut off, then you can still transmit out of your particular area using radio and get a message through. Sometimes the infrastructure's unavailable, or it might have just fallen over, or been unplugged, or sometimes it might not be trusted. You might not want to send a message, even an encrypted one, through a channel due to various sorts of attacks when someone else is owning all the infrastructure and controlling it. If the software and hardware is open, then it can be audited quite easily. If you're relying on a binary blob to send your information, then you're not really quite sure what's going on, what other messages are coming out from that binary blob. But if you can see the software and the hardware, then you've got a pretty good idea that it's what you think it is and not what someone else would like it to be. Once again, if we can get a lot of the complexity in open software, then the hardware becomes simpler, and it becomes so simple that you or I can assemble it, or at least understand it, and then any sort of physical intrusion will be obvious. If someone inserts a little board in my laptop here, I might have a hard time finding it because it's a fairly complex motherboard, a bunch of chips I don't understand anyway. But if someone tries to tamper with a simple radio that I understand and I've got the circuit diagram for, it's going to be a lot more obvious. So it takes away less of a risk of physical intrusion. A lot of this talk is about implementing on a microcontroller. Now, they can be reflashed at any time from trusted sources, for instance, our own build. So it takes away the risk of someone flashing it with a version that may not be as secure as we would like. So you could even reflash the thing every time you switch it on, just to make sure. Okay, so why do we want to go embedded? Currently, to run this system, you needed a minimum laptop and a radio like this. This is a small one. It's got a fairly low transmit power, only 5 watts. It's marginal for this sort of application. You really want 20 or 100 watts. So those radios are like this. So you're talking about a fairly big package you've got to carry around at the moment to do this open source digital radio. What we'd like to get it down to is maybe just the radio with a digital mode with an embedded chip inside it, or even in the VHF form factor as the SDR Whitebox example. So smaller form factor, ease of use. At the moment, you require 2 sound cards. One connects to a headset for you, the other the audio interface to the radio. It can be fiddly to set up. There's USB stuff involved that devices come and go as you plug and unplug things in. And you've got to set the sound levels right. So it is a bit messier to set up at the moment. So the idea is to come up with something embedded that runs on a microcontroller and eventually embed that into the radios. And there's also some possibility in reverse to embed some of the radio functionality into the microcontroller and simplify the radio. Low cost and low power. We'd rather use a $20 microcontroller than a $1,000 PC if we can avoid it. And getting it to the point where it's easy to use, cheap, and hopefully as good a performer as analog methods will allow widespread adoption and pickup of open source radio technology, which is what we're aiming for here. So the microcontroller I'm using is this one, the STM32F4. The way I use it is on one of these little discovery boards here. You're welcome to come down and have a look at it. They're $18 or something. Has a bunch of peripherals, but mainly just the STM32 chip. It's an ARM4, roughly sort of capability of a router in terms of its MIPS and things, plenty of flash and RAM. It's got an FPU, a floating point hardware unit. That's pretty important for the work I do. Codec 2 doesn't have a fixed point port, only floating point, so that makes it much easier to run. It's got loads of peripherals, this chip. A monster data sheet. Just to make GPIOs flash, you need 8 or 9 register programs and things like that, because it's so flexible and so many things you can do. So a bit of a steep learning curve. It's not like using a pick or something like that, or a simple AVR. There's a fair bit more to it. But fortunately, there's plenty of examples around, and eventually we can get going on it. It's the GCC toolchain, all the compilers, debuggers, etc. Low-cost development boards. The reason we chose this was a couple of other guys started using it on the Codec 2 mailing list, so I thought I'd follow them. I didn't do any particularly wide survey of other chips that are available. Just wanted to have a go of this one. Seemed to be the right one at the time. Those gentlemen, Peter and Sergi, so thanks to them for helping start this project off. Okay, so porting to the microcontroller. It wasn't quite as easy as simply recompiling the C code to run on the microcontroller. Some subtle changes were required. This is the input and output to Codec 2 are speech waveforms. It's not like a binary stream. So the problem is with speech is the only way you can test the quality of it is you have to listen to it. So you compare, say, the output from the host PC compared to the output from the microcontroller. How do they sound? Is one better than the other? Is there a subtle bug in there? That drives you nuts after a while, because the ear's not very good at distinguishing these sorts of things. So we need an automated way to say that, okay, I've had to modify the code slightly for the microcontroller. Is it still okay? How do we verify that the port is working? So the sort of approach I've taken is to diff the input and output samples, but that sort of has to be done in an intelligent way. There are some difference in the input and output waveforms that the ear can't hear. For example, different chips tend to have different implementations of the RAND function. I use that to generate white noise in the synthesized speech. Now, white noise doesn't really matter how you develop it. It's going to sound the same, but the waveform might be very different if it comes from a different algorithm. So some things like that, you've either got to make sure they use the same algorithm to make it easy to test sometimes, or make an intelligent decision that, look, it is different there, but that's okay. So given I wrote the codec, that gives me a little bit of a head start and that sort of thing, and knowing what matters and what doesn't. The microcontroller has no operating system. It's bare metal, so it's just running the codec in a loop, or maybe in line with some other code like the radio code or the modem code. So that means it's got no file I/O. It does, however, have access. We've got debug access via USB and via GDB support. So you have a GDB server running on the host PC and a little bit of firmware on the board that lets you access memory locations and things. So what I've done is written an I/O subsystem, basically a subset of the standard I/O system for the microcontroller that uses the host PC's peripherals. So when the microcontroller code says printf, something prints on the PC screen. And that makes it a little bit like using command line GCC debugging. So, you've just got the console, things print out, things get saved to files. That's all I have to worry about. I don't have to worry about moving memory buffers and GDB things on the microcontroller to see if it's working okay. So it turns it into command line GCC debugging.
Are you doing the A to D on the board, or are you just sending web samples?
Yeah, for the purpose of verifying the codec, I'm just taking my usual standard samples and processing them and comparing them to what the host PC does and verifying that they're the same. So this technique, I actually first did it 20 years ago for a really early DSP board, and it was an Isobus sitting in an old XT PC or something, and I copied the idea for another guy, and I thought of using it again, but then I figured a bunch of other guys must be doing this, and I looked it up, and it's called Semihosting, so I found something out, but I've been doing it for 20 years but didn't know what it was called. So what I've built is another semi-hosting system. So what will happen is Codec 2 will do a file I/O or printf or something like that. There's a little test program calling the Codec 2 library, which will drive the standard I/O library, which will be monitored by the GDB server and some little firmware on the discovery board that allows you to access memory locations. And then the modified GDB server will then send things to the display or disk or do disk I/O. So I had to modify, as well as writing the code for the discovery, I also modified the GDB server code a little bit to support this. This is an example of the standard I/O printf implementation. So printf can have a variable number of arguments that are passed to it. So all this code is just standard sort of C code that takes those variable arguments and prints the whole printf string to a memory buffer inside this function. And then we communicate the location of that buffer to the host PC. So these are just two globals. The first one points to the string, the second one says how long the string is. So by this time, it's the printf, the whole string's been rendered by the built-in VSN printf function. We set up those globals, and then this is another one that the host PC is monitoring at a polling loop, and that's normally set to 0. But when we want it to do something, we set it to some sort of constant. That means, in this case, go execute a printf for me. The host PC sees that, goes and reads these globals, and pulls the string out of the memory of the microcontroller, prints it, resets this global here, and meanwhile this thing's sitting there waiting. It's pretty slow, but it works, and speed's not an issue for what I'm doing. I just needed that I/O to make my debugging easier. So that's the printf. There's also similar implementations for a bunch of other standard I/O functions that I needed. So we can show you this working. I apologise if the font's a bit small there. First of all, this is the GDB server. So this server runs on the laptop, in this case, the host PC is the laptop, and interfaces to the firmware that's on the target system, the microcontroller. Down here we've got GDB running. I connect to it, to the server, and now we're ready to go. Hit C for continue, and now you can see in the GDB server window, that's a bunch of printfs coming out that's printing out diagnostics information. In this case, I'll just stop that so we can view it. In this case, it's a bunch of timing measurements. I've got some code that can timestamp various algorithms as the DSP algorithms are executing. So, for example, up here, the encoder's taking 10.9 milliseconds to execute. It's got 40 milliseconds available to it, so that's taking about a quarter of the CPU of the microcontroller. And down here, the decoder's 23.9 microseconds, and this is a bunch of algorithms in the decoder. So just by printing these out, I could profile it, then go to work on the various algorithms. And it's also saving those raw files. The STM in is the input speech file, and the STM out is the output speech file. One thing I haven't worked out to do is pass command line arguments to main through this system, but so I just have to use fixed file names. And then I can play them or plot them on the screen. Can also dump state variables to text files, so I can examine internal states of functions. The tools are a bit clunky. I wrote them myself just for this job really, but they're usable. Semihosting made it really easy to test and verify the algorithm. Otherwise it would have been really hard, just comparing memory buffers and things. I developed macros to profile the code and to dump state. Sometimes if I was getting the wrong answers, I'd have to dig down to one of the signal processing algorithms, dump the values, compare them to a similar dump from the host one and work out what was going wrong. A lot of the changes were things like just converting doubles to float functions. The FPU's a single precision float on this microcontroller, whereas the PC's double precision. And I tracked down a bunch of small differences. A lot of the cases, I didn't think there was anything wrong, but you want to be sure. You let a little bug get in and it creeps in, you don't know whether there'll be some strange behaviour down the road. Also found some bugs in the codec that I'd missed on the host PC version. Just little things like uninitialized variables that happen sometimes when you compile it on another processor. So that was useful. And some differences like round-off errors, rand function, things like that. A lot of the work involved, I'd find something was too slow and identify a little bit of source code in a function, just rewrite a for loop in a different way, pre-compute some values rather than computing them every time, and eventually we got it fast enough. It started off at about 10 times real time, and we got it down to about 80% of real time at the moment, and plenty more could be done by modifying. I didn't actually modify the algorithm at all, just made what was there run faster. But I've got some ideas to move some algorithms from the time to frequency domain and back again to speed them up a little bit. Some of these signal processing algorithms, there's various ways to execute the same thing. Sometimes it's easier to view them in the time domain, the problem, like the spectrum of the signal, and other times it's better to process the time domain signal. So you can do it both ways, and one way is sometimes faster than the other. So this is an example of the sort of files that get dumped out of the system. This is a 3-second waveform, speech waveform, and they look pretty similar. The top one's out of the PC, the bottom one's out of the microcontroller. When you diff them, There's small differences. You can see the maximum difference there is about 300 units out of, well, 30,000 or 25,000 is the peak there. So very small differences, and it turned out they were not significant, so I could leave them in there. Okay, so while I was doing this and noticed how powerful microcontrollers had been since the last time I played with them, I started wondering, can we embed some of the radio functions into the microcontroller? Do a little software-defined radio project, but on the microcontroller. Typical software-defined radio architectures typically have FPGAs, heavy-duty processing, but I wanted to see if we could do the whole thing in, in a low-end software device. It is fast enough to do DSP. Clearly, it's running Codec 2, and that's a fairly serious DSP algorithm. So I wanted to know if we can build a radio with it. Can we take this board and with a few analog components hook an antenna up to it and make it into a radio? I mean, the holy grail for software-defined radio is the antenna and then the analog-digital converter, and everything else is software. All the hardware that's in one of these boxes gets replaced by a computer program, except for the antenna connector. So software can be free, completely free, as in beer, especially open software. These things are cheap, and with a few bucks of analog components, can we make a $30 HF digital voice terminal rather than a $800 or $900 radio? We might even be able, one thing I've been thinking about for a while, especially with my friends in the developing world, is using a microcontroller plus e-waste to manufacture a communications device. A whole lot of analog TVs floating around there with RF components in them. Even PC power supplies have chunky power transistors and coils and things that will work quite well at HF. So it could be possible to make a communications device from junk. So this is a block diagram of Codec 2 as a receiver. I haven't got this going yet because I only got this brainstorm a week ago. So I was hoping to have something running for LCA, but I had a lot of fun and I'm learning a lot about, I'm not real good at the RF side, so I'm learning about that sort of stuff. But everything in bright blue I've worked out can be implemented in the microcontroller. So for those of you who are not too familiar with how radios work, just briefly what happens is you pick up the signal on the antenna here. There's something, in this case we're designed for the 7 megahertz frequency range, just a small part around 7 megahertz in the HF radio spectrum. Have a bandpass filter that knocks out all the other frequencies, just leaves a little slice of 7 megahertz. Then we have something called a mixer that mixes this 7 megahertz signal down to, say, an intermediate frequency at around 100 kilohertz that we can then sample in the analog to digital converter, put it inside, then now it's in software. So from then on, everything in bright blue we do in software. One neat trick was I worked out I could use the timers on the microcontroller as the analog local oscillator. Normally that's a little electronic circuit, but I can use the timers because this thing clocks so fast to be the mixer for the signal. So there's some more down conversion to baseband. We go through the demodulator, a Codec 2 decoder, out a digital analog converter, and then we're back into analog land for the speaker amplifier and speaker. But just about everything, as you can see, can be done in software. So I'm currently, I guess, working through some of these components now and having a bit of fun.
So traditionally, what you're essentially got there is a superhet receiver.
Yes.
And traditionally, the point of a superhet receiver was to prevent noise getting in, and so you mix it down to intermediate frequency before you go down a baseband. I know there are a lot of SDRs that are on the market now that are going direct to baseband before they go to the ADC. Why have you chosen to use an intermediate frequency rather than go straight to baseband?
Unless we do the quadrature down conversion, the conversion to I and Q in software, which means it can be perfect, rather than using two analog mixes interface and the quadrature parts. So I hope that's come up all right. I've got this in front of me, but that's where I'm at with it. That's that's all the parts are. That's about an hour's work, including winding the coils. This is the bandpass filter up here. These diodes here do the mixing. This other coil is where the local oscillator gets injected from the microcontroller, and this little wire here is the input to the analog digital converter. So that's potentially, could be enough to receive a signal off the HF radio spectrum. We shall see. Recent work. So just to summarise, over the past 12 months, we released FreeDV and improved the robustness, and thank you very much to all the hams around the world and Australia who have helped me with that. Experimental Android port by our very own Joel Stanley, sitting up the back there, who talked about last year's LCA. That's worth a look because it explains a bit more about radio theory as well. The handheld SDR Whitebox by Chris Tester, and Bruce Perenz is involved in promoting that effort. He's quite serious about it. And Codec 2 has been ported to a microcontroller, and I would like to acknowledge a mystery company who supported that work. It was some contract development. Because they're a commercial company, they wish to remain anonymous, and I respect that, but I did want to acknowledge their input, so thank you. Next 12 months, hopefully we'll have some fully embedded FreeDV. I'm working on improving the robustness on HF channels even further, targeting a better than analog SSB quality, and hopefully we'll have an SDR handheld Whitebox product released. So that's the end of the talk, and opening up the questions if you like. Yes?
Has there been any work on moving Codec 2 onto some of the...
Yeah, there is a lot of talk about VHF mode, and some protocols have been designed, even some modem code available. No one's really put it all together. What would be possible as a first step is just simply to bundle some of this code up in FreeDV with another mode and plug, using the Sound Blaster interface, plug it into a VHF radio. So that's something that's we're waiting to, someone's really just got to do it, that's all.
There's lots of arguments on the mailing list as to which FM digital mode they should be using and at what bit rate.
Yeah, there are a couple of mailing lists for this stuff. Digital Voice mailing list, Google Group, and Codec 2 mailing list, where people debate those very questions with lots of passion. Yes. I beg your pardon? Okay, the question was, is there a VHF radio mode for Codec 2? Thank you for the reminder. Yes?
Is there any work being done on higher bit rate open codecs?
No, not that I, for over, say, radio.
Over radio?
Yeah, not that I know of, but there are a subset of people who are interested in, say, wideband SSB and AM radio, and some people have suggested there is a market for that. The actual analog bandwidth is only about 1.2 kilohertz of this signal. It's much narrower than SSB. So there's room in, say, a given narrow band SSB bandwidth to have higher quality radio if you've got the signal to noise ratio to support the bit rate required. So it doesn't break. You don't want it breaking up in bit errors if you're trying to get higher quality. Yeah. Yes?
It's like CT/CSS tones, how outside with the modem signal or embedded inside?
Yeah, that'd probably turn into part of the digital protocol. So there'd be a bit in there, that the repeater receives rather than a separate analog tone.
Like a NAC code.
Yeah. Yeah, that'd probably be part of the protocol. Also, these digital protocols sometimes have your call sign in there, and whether it's to go to a repeater and things like that. Yes?
You mentioned that floating point is required. Is there any plans to possibly look at fixed point DSP implementation?
Yes, a lot of people have been talking about it, and there was a little bit of work done by a student this year to port a few of the modules into fixed point. So something of an ongoing effort. I'm of mixed, it's a lot of work, and then you've got to maintain it, and a lot of things are coming out with FPUs these days. It's just transistors, and they're cheap, so I don't know. I'll do it if someone pays me a lot of money. Yeah.
It sounds like you still have a bit of headroom even on this microcontroller. You could do that kind of stuff, right?
Oh, we'll think we'll generally run faster if we put a fixed point. Yes, and there's still plenty of room for making the code run faster and to get other things running on the microcontroller. And I'm sure there'll be other faster microcontrollers. Yes, sure.
The M3 that's in the Smart Fusion that Chris is using doesn't have floating point. How does he plan to make
I
code?
think they're going to do it with a board.
Saving so?
Some sort of Torah board,
Right.
or possibly if they can get the funds arranged to port. I think that M3 is designed only for control rather than signal processing. Yes.
Are you planning to implement the modem into the microcontroller as well?
Yes.
So it'll be a straight plug into your...
Yeah. Yeah, maybe a little box, even something in the microphone form factor. Plug straight in.
Going on from that, how does it sound if you're, moment you're sweeping a frequency range, you can hear when you're coming up on the station, it's either a low or a high tone, and as you get closer, it becomes more intelligent.
No, basically if the modem locks, you get the audio, otherwise it's silent.
So will that make it more difficult to find other stations?
It's actually pretty easy to find, and you can see it very clearly on the spectrum, and it's continuous, unlike an analog voice. Also, it's got an automatic frequency control, so you get within 200 hertz and just bang, it's on. So you can even, if you've got a crappy old receiver that drifts around, it'll track that quite heavily.
Will that make it difficult to discern between two close stations and remove the advantage of being narrowband?
If they're overlapping, you could have some trouble because you're trying to sync if they're really close, like with the pilot tool and 200 hertz. Apart from that, you can just grab one of them. And
then once you QSY enough,
yeah, and it can handle interference from other analog people. And if your signal's a few dB above the interferer, it won't pick up the interferer. A little bit FM issue.
I quite like the direct listening analog sound. You're pretty close to tweaking it. You could have it sound exactly like the Imperial Battle Language and stuff.
That would be a neat feature.
You mentioned there's different versions that have obviously as it's progressing. Have you been trying to maintain backward compatibility?
Yes, on the side there was a modem, one was a big 0.1 modem, for example. That we found several bugs in the code and fixed them, but because we released the software, we had to make sure the bugs were still implemented.
The protocol is now basically locked down. You're just tweaking and improving the.
Well, I'd like to push the improvements in the quality, so the robustness, so I can handle low signals, noise ratios.
You think it's going to break further?
Oh yeah, it'll break what's there now. But it's still pretty experimental. And amps don't mind. Yes.
While I was following your ongoing efforts to improve it, I was interested it was just all largely heuristic listening initially.
Yeah, a lot of it is.
Can you tell us more about the methods of automating that sort of testing?
Really, it's just listen to it and how bad does it sound or how good. It's horrendously manual. There are some parts of the algorithm that you can put objective tests on, like you can measure the distortion between two different versions of the
So
process.
you can try looking at things like NFT breakdowns of your
Yeah,
issues and
it does. I mean, basically that's part of the signal processing. Some things like the modem are easy to measure signal to noise ratio versus bit error rate. But yeah, for the speech stuff, yeah, I've even got an equalizer in there that people can program the frequency response, and they can tweak little knobs inside the algorithm. So I threw that out there and let people play with it and see what they like the best. Because sometimes I don't know why he's the best. Yeah. And sometimes I think it sounds like crap and everyone says how good it sounds compared to other stuff. So who am I to judge it?
I'd just like to thank our speaker, David Rowe, coming down and sharing
thanks for coming to speak at the con.
Woohoo! Thank you. Awesome.